Today we're going to be talking about the Lambda architecture and how to say goodbye to this architecture. I'm going to present myself. My name is David Regalado. I recently joined a startup where I serve as a VP of engineering. We're building an awesome product using generative AI. Since we're operating in stealth mode, I cannot disclose the name of the company right now. But what I can tell you is that I'm a Google Cloud Champion Innovator. The Champion Innovators is a global network of more than 500 professionals who are technical experts in the Google Cloud products and services. We do not work for Google, but to join this elite group, we should be nominated by Googlers. I'm the founder of the Data Engineering Latam community, the biggest, fastest growing community in Latin America. I'm also an ambassador at AI Time Journal. This organization publishes articles, podcast interviews, and ebooks with insights from industry leaders and experts, and use cases of exponential technologies across multiple fields. Okay, let's talk about a theory of everything. A theory of everything is an hypothetical, singular, all-encompassing, coherent theoretical framework of physics that fully explains and links together all aspects of the universe. Finding a theory of everything is one of the major unsolved problems in physics. Over the past few centuries, two hypothetical frameworks have been developed that together most closely resemble a theory of everything. These two theories upon which all modern physics rests are general relativity and quantum mechanics. General relativity is a theoretical framework that only focuses on gravity for understanding the universe in regions of both large scale and high mass. Planets, stars, galaxies, clusters of galaxies, etc. On the other hand, quantum mechanics is a theoretical framework that only focuses on the three non-gravitational forces for understanding the universe in regions of both very small scale and low mass, subatomic particles, atoms, etc. Quantum mechanics successfully implemented the standard model that describes the three non-gravitational forces: strong nuclear, weak nuclear, and electromagnetic force, as well as all observed elementary particles. In Einstein's day, the strong and weak forces had not been yet discovered. Yet he found the exponential existence of two other distinct forces, gravity and electromagnetism, far more alluring. This launched his 40-year voyage in search of the so-called unified field theory that he hoped would show that these two forces are really manifestations of one grand underlying principle. Decades later, with the appearance of strong and weak forces, new theories emerged trying to unite them into a single one. But enough physics. We are here to talk about data, but you'll see that having a theory of everything is not a nice to have, but a must have in our projects. What we have here is the Lambda architecture. The way this works is that an immutable sequence of records is captured and fed into a batch system and a stream processing system in parallel. You implement your transformation logic twice, once in the batch system and once in the stream processing system. You stitch together the results from both systems at query time to produce a complete answer. The problem with the Lambda architecture is that maintaining code that needs to produce the same result in two complex distributed systems is painful. Programming in distributed frameworks like Storm and Hadoop is complex. Inevitably, code ends up being specifically engineered toward the framework it runs. The resulting operational complexity of systems implementing the Lambda architecture is the one thing that seems to be universally agreed on by everyone doing it. This poses a problem for organizations since it takes time to hire an engineer who meets all these skills of a group of engineers who together cover these skills. And on top of that, there is always the danger that they will leave for another company that pays more. You can try upskilling your data team, but it will take time. And on top of that, there is always the danger that they will leave you for another company that pays them more. Your competition can leave you behind if they are able to solve this problem before you. And they may be the company that offers your engineers the most money. It was a nightmare. Duplicate data and logic. Data in the Lambda architecture is written twice, leading to duplicated logic and implementation in both the speed and batch layers. Dual execution paths. The architecture requires separate execution paths for streaming and batch, creating a maintenance challenge with multiple frameworks, components, and clusters. Code divergence. Lambda architectures often results in code-based divergence, as bad code works on finite datasets, while real-time stream processing operates on an infinite event stream. Diverse skill set requirement. Managing the platform demands developers with diverse skill set, diverting attention from core business problems. This slide depicts very well how it feels for the engineer to keep up with different technologies for each use case. At one time, you have to learn C, but for other use cases, you will need R. Maybe later, you will need to do some Python codes or then implement some Java. And what about the frameworks? What about the big data frameworks? There is Hadoop, there is Hive, there is Spark, there is Flink, and many others. You see where this is going, right? It kind of feels like playing the whack-a-mole game. So no one wants to waste their time either searching for talent, training in-house teams, or learning technologies over and over again instead of adding value to the business. Nobody wants duplicate data and logic, dual execution paths, code-based divergence, or diverse skill set requirements. So the solution must be to replace this Lambda architecture, right? How so? How do we solve this problem? What are we missing? Introducing the unified Apache Beam model, the easiest way to do batch and streaming data processing. Write once, run anywhere. Data processing for mission-critical production workloads. While with Lambda architecture, data engineers are forced to master a set of technologies for data processing, with Apache Beam, you can do the same, but in a simplified way. The unified programming model consists of the following. Batch processing and streaming processing are the processing type, and we will see later that with Beam, you no longer have to think on the Lambda architecture scenario. Every big data processing framework like Apache Spark, Apache Flink, Google Cloud Dataflow, etc., is an execution runner, and the implementation details are transparent for the developer. meaning that it just works. Every programming language like Python, Go, Java, SQL is a SDK for writing Beam code. BigQuery, MongoDB, Elasticsearch, S3, Cassandra, Redis, and many, many more are the sources and sinks for the Beam model, provides the corresponding I/O connectors. These are code snippets to calculate a sum per key. No matter which SDK you choose to write your code, it is translated, interpreted into Beam model, and then sent to the runner of your choice. Let's talk about the Beam features. Unified because it provides a simplified single programming model for both batch and streaming use cases. Extensible because other projects have been built on top of Beam, like TensorFlow Extended and Apache Hub. It is open source with a community-based development and support to help evolve your application and meet the needs of your specific use cases. It is portable because you write your code once and then you're free to run it anywhere. Now, because you can write your code in the programming language of your choice, and because Beam understands what you are trying to accomplish, you can create multi-language pipelines. Picture this. You have a big project that involves geographically distributed teams with different skills and tech stack. Some program in Python, others in Java. With Apache Beam, you can have them all working on the same project because the transformations or business logics created by the team A can be reused by team B. Who uses Apache Beam? Apache Beam is used by LinkedIn, is used by some major banks and other big companies, and the results that they are reporting is something like we handle trillions of events daily, we reduce time by X times, and we reduce cost. So it is really have been getting a little traction. Some of these users are really, really happy implementing this way of programming. Okay, the evolution of Apache Beam. Google published the original paper on MapReduce in 2004, which fundamentally changed the way we do distributed processing. This paper described a generalized solution for specifying logic that runs in parallel across multiple machines while shielding the author from dealing with low-level details like moving data between machines and handling fault tolerance. At this point, things diverge a little bit. Inside Google, engineers kept innovating, but within a relatively homogeneous environment. In this environment, there were limited file formats to deal with, only a handful of languages and standardized tooling. This meant Googlers were able to focus on refining the core methodology. Google continued to publish papers about these ideas, which meant non-Googlers got lots of PDF to read, but not much concrete to play with. Outside Google, the open source community created its own MapReduce implementation in Hadoop. An entire processing ecosystem developed, and occasionally some of this was influenced by those Google papers. Google announced the Google Data Flow, which was based on technology that evolved from MapReduce, but includes newer ideas like Flume Java improve abstractions, and mill will focus on streaming and real-time execution. Google Cloud Dataflow included both a new programming model for writing both batch and streaming data processing pipelines, as well as a fully managed service for executing them. In 2016, Google, along with a handful of partners, donated this programming model to the Apache Software Foundation as the incubating project Apache Beam. In December 2016, Apache Beam graduated as a top-level project at the Apache Software Foundation. Apache Beam's programming model uses higher-level abstraction that lets you focus on your application logic, not how to cram your application logic into an underlying framework. Instead, you build a pipeline as an arbitrary graph that mixes custom element-wise processing with aggregations and library functions. Beam pipelines can process both bounded fixed-size datasets as well as infinite streams of elements. And when you write your application logic, you don't need to worry which type of collection you'll be processing. This makes your pipeline and logic very flexible and reusable. Now, to truly unify batch and streaming processing, we need to separate the notion of event time from processing time. Event time is the time an event happened. So, for example, if we're processing scores from a mobile gaming application, that will be the time that the user popped the balloons or crashed the candy or whatever it is they are frantically doing. But that event time may differ from the time the element is processed, even in real-time system. This graph shows a sample dataset of points scored for a specific team in our hypothetical mobile gaming application. On the x-axis, we had event time, and on the y-axis is processing time. If everything was perfect, elements would arrive in our system immediately. So we'd see things along this dashed line, but distributed systems don't often cooperate. Sometimes it's not so bad. Here, this event from just before 12 and 7 maybe just encountered a small network delay and arrived almost immediately after 12 and 7 minutes. But this one over here was more like 7 minutes delayed. Perhaps our user was playing in an elevator or in a subway. So the score is delayed by a temporary lack of network connectivity. And the margins of this graph can't even contain what we see if our game supports an offline mode. If a user is playing on a transatlantic flight in an airplane mode, it might be hours until that flight lands and we get those scores for processing. These types of infinite out-of-order data sources can be really tricky to reason about, unless you know what questions to ask. The Beam model is based on 4 key questions. What results are calculated? Are you doing compute sums, joins, histograms, machine learning models? Where in event time the results are calculated? How does the time each event originally occur affects the results? Are results aggregated for all time in fixed windows or as user activity sessions. When in processing time, the results are materialized. Does the time each event arrives in the system affect the results? How do we know when to emit a result? What do we do about data that comes in late from those pesky users playing on transatlantic flights? And finally, how do refinements relate? If we choose to emit results multiple times, is each result independent and distinct? Do they build upon one another? Let's take a quick look at how we can solve these questions to build a pipeline. Here's a snippet from the pipeline that processes scoring results from a mobile gaming application. In yellow, you can see the computation that we are performing, the what. In this case, taking team scores pairs and summing them per team. So let's see what happens to our sample data if we execute this in traditional batch system. In this looping animation, the gray line represents processing time. As the pipeline executes and processes elements, they are accumulated into the intermediate state, just under the processing timeline. When processing completes, the system emits the results in yellow. This is pretty standard batch processing, but let's see how answering the remaining 3 questions can make this more expressive. Let's start by playing with event time. By specifying a window function, we can calculate independent results for different slices of event time. For example, every minute, every hour, or every day. In this case, we will calculate an independent sum for every 2-minute window. Now, if we look at how things execute, you can see that we are calculating an independent answer for every 2-minute period of event time. But we're still waiting until the entire computation completes to emit any results. That might work fine for bounded datasets, but we'll eventually finish processing. But it's not going to work if we are trying to process an infinite amount of data. So what we need to do is reduce the latency of individual results. We do that by asking for results to be emitted or triggered based on the system's best estimate of when it has all the input data. We call the estimate watermark. Now the graph contains the watermark drawn in green, and by triggering at the watermark, the result for each window is emitted as soon as we roughly think we're done processing data, seeing data for that slice of time. But again, the watermark is often just a heuristic. It's the system's best guess about data completeness. Right now, the watermark is too fast, and so in some use cases, we're moving on without all the data. So that user who scored 9 points in the elevator is just playing out of luck. Those 9 points don't get included in their team's score. But we don't want to be too slow either. It's not good if we wait to emit anything until all the flights everywhere had landed, just in case someone in seat 16B is playing our game somewhere over the Atlantic. So let's use a more sophisticated trigger to request both speculative early firings as data is still trickling in. and also update results if late elements arrive. Once we do this though, we might get multiple results for the same window of event time. So we have answered the 4 questions about how refined results relate. Here we choose to just continually accumulate the score. Now, there are multiple results for each window. Some results, like the second, produce early incomplete results as data arrives. There's one on-time result per window when we think we pretty much got all the data. And these are late results if additional data comes in behind the watermark, like in the first window. And because we choose to accumulate, each result includes all the elements in the window, even if they have already been part of the early result. So we started with an algorithm that we wanted to compute. In this case, it happens to be an integer summation, but so that it can reasonable to animate. But it could be a much more complex computation. And just by tweaking just a line here or there, we went through a number of use cases, from the simple traditional batch style to an advanced streaming situation. Just like the MapReduce model fundamentally changed the way we do distributed processing by providing the right set of abstractions, this model changes the way we unify batch and streaming processing. Today, Apache Beam includes the core unified programming model revolving around the what, where, when, how questions, the SDKs for Python, Java, Go, TypeScript, Scala, and SQL, and most important for portability, multiple runners that can execute Beam pipelines on existing distributed processing backends. The goal in Beam is to fully support 3 different categories of users. End users who are just interested in writing data processing pipelines. They want to use the language that they want to use and choose the runtime that works for them, whether it's on-premise, on a Zoom cluster on the clouds, or on a fully managed service. In addition, we want to develop stable APIs and documentation to allow others in the open source community to create Beam SDKs in other languages and to provide runners for alternate distributed processing environments. While we love to have a world where all the runners support the fully suite of semantics included in the Beam model, practically speaking, there will always be certain features that some runners can't provide. To help clarify things, Beam's website provides a capability matrix where the key features of Beam model are enumerated for all existing runners, categorized around the 4 questions addressed by the model. This table is maintained over time as model evolves. The understanding grows and runners are created or features added. This is the Beam Playground. It is a web interface that includes code examples for different Beam concepts and for different SDKs. You can see the code, the output, and a graph depicting each stage of your pipeline. This is the tour of Beam. It is a web interface that will walk you through each of these Beam concepts from basic level to advanced level. This is where you'll find all the theory so you can master Apache Beam programming. Feeling ready to try it on your local machine? Clone the Beam started repo to get started. There are more repos available per each of the programming languages that Beam supports. Here are the similarities between PySpark and Beam. You can find the complete table on Beam's official website. You can see there are functions like map, filter, group by key. So by using Apache Beam, we can reduce costs by maintaining just business logic and not worrying about how to cram business logic into an underlying framework. The need for diverse skill sets reduced dramatically. We don't have to spend our time thinking about different data architectures and data processing frameworks. It just works. We can get our time back as engineers. No more whack-a-mole game. So this is what I call the theory of everything for data processing. I encourage you to visit and bookmark these URLs. With that, we come to the end of the presentation. Scan this code to connect with me. I'll be happy to talk about Beam, AI, or physics. Thank you.